So in this video and in the next three, I want to talk about some applications of first order differential equations, particularly of the sort that you've been learning about, namely separable equations. Differential equations are eminently applicable to the real world. They are really, really useful for modeling various phenomenon in the real world. The one we're going to talk about today is Newton's law of cooling, which explains or seeks to explain or seeks to model how a object's temperature can change when it is exposed to a space of a different temperature. Okay. We'll also talk about radioactive decay of radioactive isotopes in another video. That's an application that first order separable differential equations are suitable for. We'll also talk about something called Torricelli's law, which will explain what happens or how can we account for the change in volume if we have a big barrel of fluid and we put a hole in the side of that barrel of fluid, right? So there's something called Torricelli's law, which explains that. And finally, we'll talk about something called mixing problems, which are, sort of a favorite of differential equations class, such as this one. Okay, but we did start last time, we did end the last video talking about a Newton's law of cooling problem here, and you can read it. I don't want to read it. Go ahead and read it. Basics though, if we have an object whose temperature is capital T, depending on little t, sitting in a space with ambient temperature fixed at A, then we have dt, the rate of change of the temperature, is equal to K. And I don't think I said it explicitly, but it is the case that K is a positive constant of proportionality here, times A minus T, the difference between the ambient and the object's temperature. Now, just some notes to record about this equation here. Note, if A is greater than T, well, actually, let's start with the situation that we actually have in front of us. If A is less than T, so meaning that the object's temperature is greater, it's hotter than the ambient temperature, then will you acknowledge that A minus T is going to be a negative quantity, and therefore dt is negative, which of course implies that T is decreasing. We learned this when we learned about basic properties of the derivative. And similarly, if A is greater than T, then dt is positive. I mean, just look at it. If A is greater than T, then A minus T is positive. K is taken to be positive by assumption. And so this equation is asserting that dt is going to be positive. And of course, positive first derivative means that T is increasing. So think about what this is saying. This is saying that if you take an object whose temperature is smaller, is lower than that of the ambient space, that temperature is going to warm up. Like Adoy, right? This explains why, when you get that ice cold Coke Zero out of the fridge and you leave it out in your room, it approaches room temperature. Okay, it gets, well, sorry, no, it doesn't explain quite that much, but it does at least explain why the temperature of that Coke Zero goes up. Okay, I went through the steps of solving this differential equation here in full generality, as I've done here, and you can see the previous video for that. Maybe one thing that I want to say, which is a little bit technical, but kind of is important to say. There's a crucial step in these separability problems where I'm dividing both sides by this A minus T. And you all are careful students of mathematics, and you know that this should send up maybe some red flags. Because what if A minus T is 0, right? What if A minus T is 0? Now, if A minus T is, don't forget, T here is a function of time. if a minus t is 0 for all time, okay, this makes things very easy to understand. If a minus t is 0 for all time, that means that t is equal to a for all time, right? A minus t being 0 means a is equal to t. Okay, that's not exactly surprising, but if a is equal to t for all time, then of course the rate of change of that of the temperature is going to be 0. Okay, so that, in other words, what I'm trying to say is that a minus t is 0, then we get a kind of very commonsensical, easy to understand solution out of that. Call it the trivial solution, right? It's a very trivial solution in which indeed a is equal to t for all time. If this amounts to me saying, if a is equal to t for all time, then a is equal to t for all time. So it sounds really stupid and vacuous because it kind of is, all right? But more subtle is if a is ever equal to t. If the temperature is ever equal to that of the ambient temperature, what is happening? Are we still allowed to divide by a minus t? I mean, yeah, we can kind of do whatever we want, right? But we want to make sure that what we're doing makes sense. And now this is where the existence and uniqueness theorems come in, okay? Because if if there is some time where t is equal to a, then what the existence and uniqueness theorem says is that there is a unique solution to this differential equation with that taken to be our initial condition. Like we can just think of that, like if we have for some, we'll call it t naught, we have that t of t naught is equal to a, then by the existence and uniqueness theorem, by Picard's theorem, oh yeah, Captain Jean-Luc Picard, by Picard's theorem, there's a website called ytmnd.com. This is in the early days of the internet, which was just, and it had a bunch of these kinds of things, but one of the things was a picture of Jean-Luc Picard just plastered, tiled on your web browser, and a song that just sang out Captain Jean-Luc Picard of the USS Enterprise over and over and over again. If for some t naught, t of t naught is equal to a, by Picard's theorem there is a unique solution satisfying this initial condition. And can you guess what that solution is? That solution has to be the one in which t is equal to a for all time. Do you understand what I'm saying to you? That if t of t is ever equal to a, then it will be equal to a for all time t, at least according to this differential equation here. At least according to this differential equation and Picard's theorem. Okay, so we are very, very, very safe in dividing both sides by a minus t if we simply assume that t of big T is never 0. Okay, hopefully that makes sense. It's a little bit of a niche issue, but it's one that I care about such matters, and so it makes me uncomfortable to do moves like this where I divide both sides by something where I can't be certain that what I'm getting is or where I am certain. Whatever. Okay, leave me alone. I don't like saying words out loud because words are so often meaningless. Okay, let's finish this problem. So we wrote down the general solution to the differential equation, and now we want to use the data that we have at hand in order to solve the problem, the coffee problem, because I like my coffee at this temperature and I need to know how long to wait. All right. So last time we got done saying that if the ambient temperature is well, sorry, we got done plugging in the ambient temperature being 22 degrees, and we squeezed this equation or this information that the initial temperature was 89 degrees. And from that, we were able to learn that this value of C, this constant right here, is in fact equal to 67. All right? What we haven't used yet is that the coffee is 85 degrees after 1 minute. So how can we use that? Well, hopefully this is relatively clear. We'll use that by saying, right, that 85 is equal to T of 1. T of 1 is what we get by putting in 1 in here, where C is 67 times exp of negative k plus 22. Oh, and notice that I wrote, I just set t equal to 1, and so I get this, by, sorry, that was my cat, by replacing k by, sorry, replacing by t by 1. My stupid cat distracted me. I love you. Don't look at me like that. Sorry. Okay. So, I should be able to solve this for k. No? Let's go. Let's try. So I subtract 22 from both sides and I get, what is that? 63? And I divide both sides by 67. And this is supposed to be exp of negative k. Now I take the natural log of both sides. And that's negative k. And now I'm going to multiply both sides by negative 1. Now don't forget, if you have a number in front of a logarithm, you can move that number into the power position. And so I can solve this equation just by doing this. K is equal to the natural log of 67 over 63. Think through that. If that one gives you trouble, ask me about it, okay? But anyway, this is correct. Okay, so what this says all together is that I know what T of T is for my cup of coffee. T of T is equal to, I swear to God I know. It's, 67, that's C, times exp of okay. Maybe I shouldn't have even done that because, right, negative k is what's in the general solution. So I really didn't even need to do this step. Like, okay, but who cares, right? Sort of what I'm saying. What? Okay, 67 times, so really I just put natural log of 63 over 67 times t plus 22. So just to be clear, this is what's playing the role of C, this is what's playing the role of K, and this one is playing the role of A. And my Newton's law of cooling here. Okay. Now, I'm being asked, I like my coffee when it is 60 degrees, how long should I wait? So what that translates to for this problem is, for what value of T small t gives T of T equal to, I forgot already, 60 degrees. Suppressing units. So the way that I solve this is clearly I set T of T equal to 60 and solve. So I want to solve 60 is equal to T of T, which means I want to solve 60 is equal to 67 times exp of natural log of 63 over 67 times t plus 22. So if I subtract 22 from both sides, what's 60 minus 22? No, it's 38. And then I divide by 67. So I get 38 over 67 is equal to the exp of the natural log of 63 over 67 times t. I'm going to take the natural log of both sides. Okay, so I get natural log of 38 over 67 is equal to the natural log of 63 over 67 times t. And then I solve for t by dividing both sides of this. So I get that t is equal to, and by the way, the natural log of a difference, the natural log of a quotient is the difference of natural log. So I can rewrite this as natural log of 38 minus natural log of 67 divided by natural log of 63 minus the natural log of 67. Okay. And I have no idea what that's equal to. And if I actually cared to figure this out, I would, of course, pull out a calculator. Unfortunately, I'm just way too lazy to do that. I guess I should also write the units. What are the units on this? What are the units on this? Oh, yeah, minutes, right? Minutes here. So this is how many minutes I should wait. I have no idea what this is. And I'm not enough of a nerd to pull out a calculator, even though, I mean, I wouldn't pull out a calculator. I don't actually own one. What I do have is a computer, and I'm still not going to do it. Oh, wait, will this work? Hey, Siri, what's the natural log of 38 minus the natural log of 67, whole thing divided by the natural log of 63 minus the natural log of 67? Okay.
Something went wrong. Please try again.
Oh. That didn't work. Okay, never mind then. Wait, hold on. You can stop the video now. This is all extra credit. Hold on. ChatGPT. Wait, ChatGPT doesn't know how to do math. You have to get to know your AI friends, okay? And what I know is that a problem like this, you do not want to give to your ChatGPT friend. I feel bad though, because I feel like I'm supposed to tell you the answer here, and that this is deeply unsatisfying. Is that true? How are you? Gosh, my cat is okay. Oh my god. You know what? We're just gonna end the video here. Okay, so long.